Let's apply what we've learned about Maclaurin and Taylor polynomials to actually compute, in this case, two Maclaurin polynomials. Our first case, what we want to do is we want to find the fourth degree Maclaurin polynomial for e to the negative 3x. So what we want to look at is, we have this formula here that the polynomial of nth degree is the sum from 0 to n of a sub k times x minus c to the k, where each of those a sub k's is actually defined in terms of the kth derivative evaluated at c over k factorial. So we'll compute these out. Now Maclaurin polynomials are specific. They have c equals 0. So in this particular case, this is just x to the k, and that's the derivative of the function evaluated at 0. So what you want to do here, whenever you're doing these kind of approximations, what you want to start doing is just writing out the function's derivatives just straight out. So we say, okay, the 0th derivative, that just is the function. The 0th derivative is the non-derived, it's 0 derivatives are taken, so it's the function. The first derivative here, hopefully by now you're comfortable with that derivative. We end up multiplying by negative 3 by the chain rule. The second derivative, the third derivative, and the fourth derivative. So we have, since we're doing a fourth degree Maclaurin polynomial, we take up to 4 derivatives. However, we need to evaluate those at the function point. So we need to evaluate those at c. In this case, c is 0. So that's just 1. So notice that when I plug in 0, e to the negative 3x, right, that's e to the 0. E to the 0 is 1. So what you're going to find here is all of these e to the negative 3x's, when you plug in 0, they're all just going to disappear. So you have now I say disappear, they're not 0 because e to the 0 is 1, so you're still going to have the leading coefficient. So now I have my 5 coefficients, and I can set up my polynomial. So you take your first term, and then your second term over 1 factorial. So this is really over 0 factorial. And then you have x. So normally this would be x minus c to the k, but again, c is 0. So this is x to the 1, and then plus 9 over 2 factorial x squared. So this is the second term divided by 2 factorial x squared minus 27 over 3 factorial x cubed plus 81 over 4 factorial x to the 4th. Now we can reduce this. This is going to be 1 minus 3x. So that's just going to be 9 halves x squared. Now 27 over 3 factorial is also 9 halves. It's negative 9 halves x cubed. And 81 over 4 factorial, I believe, is 27/8. So I'd also challenge you to go into like Desmos or any sort of online plotting platform and plot this e to the negative 3x and plot this as well and see how well they line up. They're not going to be perfect, but you'll be surprised that near 0, if you kind of bound it pretty close to 0, it's a pretty decent approximation. Now, for this one we have cosine of x. And we're going to do the same thing, except we're going to do a 5th degree polynomial. So it's the same process. So the 0th derivative is cosine of x. The first derivative is negative sine of x. The second derivative is negative cosine of x. The third derivative is positive sine of x. The fourth derivative is cosine of x. And the fifth derivative is negative sine of x. See a pattern here? Notice that this keeps just, it goes 1, 2, 3, 4, 1, 2, and then the next one would be negative cosine, then the one after that would be positive sine. So you end up in a differentiation cycle. Those derivatives just keep being the same. Now, for the evaluation at c equals 0, cosine of 0 is 1. Sine of 0 is 0. Cosine of 0 is 1, so that's a negative 1. Sine of 0 is 0. Cosine of 0 is 1. Sine of 0 is 0, right? Simple enough. So then we can construct our Taylor polynomial, or our Maclaurin polynomial. So 1 over 0 factorial. We'll call that x to the 0. We didn't do that before, but plus 0 over 1 factorial, x to the 1, minus 1 over 2 factorial, x squared, plus 0 over 3 factorial, x cubed, plus 1 over 4 factorial, x to the 4th, plus 0 over 5 factorial, x to the 5th. So what you see is, we're losing all of the odd terms, right? This, and this all disappear. So 0 factorial is 1. 1 divided by 1 is 1. X to the 0 is 1. So we end up with 1 minus 1/2 x squared plus 1/24 x to the 4th. So near 0, this is going to be a pretty good approximation. Partly because you know that cosine of 0 is 1. And you also know that cosine near 0 falls off, it falls off this way, right? It's almost like a parabola that's opening downward. So what you have is kind of a shifted up parabola that falls downward. And then you have this piece, which is actually the parabola that tips up, but it's so small, like 1 over 24th. So what it's really doing is, instead of falling directly down, it kind of curves. It adds a little bit of curvature, kind of what you expect a cosine to look like. So I would challenge you to go take a look at this approximation versus the cosine function, put it in a plotter, kind of see how well it matches up. You'd probably be surprised at how few terms you really need for like a sine and a cosine series to get something that's really a pretty good approximation.